Great, so let's dig into some examples here. So before I get into the examples, I wrote in here a derivative that we haven't really talked about yet, but is important and you'll need to know it for future classes and for the next few examples. And that's the derivative of the natural log, or logs in general, right? So if you're looking to differentiate ln of x, the natural log, the derivative of ln of x is 1 over x. Okay, and if you're trying to take the derivative of log base b, where the base isn't necessarily e, right? So usually if you're writing ln, so ln of x is the same as log base e of x, right? Where e is this special number, okay? So if you're trying to in general, look at the derivative of log base b of x, it's this right here, right? So it's 1 over x ln of b. Okay, so we're going to use that in the next few examples, and you'll use it for the rest of the quarter or the rest of the semester and probably the next class. Okay, so let's look at these examples, right? We're going to use L'Hopital's rule to calculate these limits. Okay, so if we look at the first one here, we've got the limit as x goes to 2 of x to the 6th minus 64 over x squared minus 4. Okay, so if you do the most obvious thing, right, which is just plugging in x equals 2 into the top and the bottom there, you're going to see that you're going to get 0 over 0. Okay, so that means you need to do more work, right? You need to do something else. So for this example in particular, one thing you could do is factor the numerator and the denominator, and then a term is going to cancel out, right? That's similar to some examples we've seen before. But let's use L'Hopital's rule to calculate this limit. Okay, so L'Hopital's rule says that calculating this limit is the same as calculating the limit as x goes to 2 of the derivative of the numerator divided by the derivative of the denominator. Okay, so let's write the derivative of the numerator. So differentiate x to the 6th, that's going to be 6x to the 5th. And then the derivative of minus 64, that's just 0. Okay, and then derivative of the bottom, so the denominator here is going to be 2x, and then the minus 4 has derivative 0, right? So we end up with something like this. Okay, so maybe let's simplify a tiny bit, right, so that we can try to take this limit. So this is the limit as x goes to 2. I'm just going to cancel in x, right? So looks like I can cut this down by 1 and then cancel this out, right? So I'm left with 6x to the 4th over, 6x to the 4th over 2, right? And then maybe cancel out that 2 in the denominator, so I'm left with limit as x goes to 2 of 3x to the 4th. Okay, so that's all the simplifying you can really do, and you can see here now you can take this limit, right? So this is equal to, okay, so plugging in now the 2 is going to give me 2 to the 4th, okay? So that now is a number, right? So you can write down whatever it is, but that gives us an answer, right? So we're no longer getting this 0 over 0 indeterminate form. Now we've got an answer, right? So now this is our limit, okay? And in particular, one thing I like to do is I like to write down where it is that I used L'Hopital's rule, right? So notice right here is where I used L'Hopital's rule, right? So in your work, you should try to highlight where it is that you used L'Hopital's rule, right? So usually I'll just write a little LH over the equal sign where I used it, okay? So let's look at the next example, right? So now we have this right here on the next page, right? So we did that one already, great. Okay, so let's look at example number 2. So now we're looking for the limit as x goes to 0 of 1 minus cosine x over sine of x. Okay, if you plug in x equals 0, you're going to see cosine of x is equal to 1. So then in the numerator, I get 1 minus 1, right? That gives me a 0. And then if I plug 0 into sine, I'm going to get 0 again. So once again, I get this indeterminate form 0 over 0. Okay, so that means that I should do more work. So for this one, it'll be difficult to try to do any algebra. Maybe you can try some other trick, multiply by the conjugate or something, but one thing you can definitely try is L'Hopital's rule. Okay, so now that we have this indeterminate form, 0 over 0, we can use L'Hopital's rule, right? So actually I'm going to write the little LH right here because I'm about to use it. Okay, so this is the limit as x goes to 0. Okay, so let's write down the numerator, the derivative of the numerator, right? So derivative of 1 is 0. The derivative of minus cosine. So here's that minus, and then the derivative of cosine is minus sine. So we have that. And then the derivative of the denominator. So derivative of sine is cosine. Okay. So we can write this as limit as x goes to 0 of, so minus, that's plus, and that's sine over cosine. And actually, I'm going to write that as tangent, right? Because sine over cosine is just tangent. And now you can see we can take this limit. So this is the same as tangent of 0. And if you think back to your pre-calculus knowledge, tangent of 0 is just 0. Okay, and that's a perfectly fine answer, right? That's a number. There's nothing funny going on with it. It's just 0, right? So that gives us a solution to this example. And remember, we started with this indeterminate form 0 over 0, right? And we used L'Hopital's rule here in this first step, did a bit of simplifying, and then eventually we're able to take the limit so that we could end up with our answer, right? So that's how you do this second example. Okay. So let's move on to the last example here. So you're very welcome to pause the video at any point and see if you can try the example on your own, right? So feel free to do that. But let's go over this one, right? So this third example. So we're looking now at the limit as x goes to infinity of ln of x over x. Okay, so if we try to take the limit right away, so ln of x, right? So if you think about the graph of ln of x, it looks something like this. Okay, so this is ln of x. And so if your x's are going to infinity, then your y values, so it's going to climb, right? It is going to get bigger and bigger. It gets bigger and bigger very slowly, but it does get bigger and bigger, right? So the limit as x goes to infinity of ln of x is actually infinity, right? It does keep getting bigger and bigger, okay? And of course, the limit as x goes to infinity of x is infinity, right? So where is x going as x goes to infinity? Well, it's going to infinity. Okay, so this gives me infinity over infinity, and this is one of those indeterminate forms, right? So that means that I can use L'Hopital's rule. Okay, so note, you really can only use L'Hopital's rule if you have an indeterminate form 0 over 0 or infinity over infinity. Okay, so that's the only time when you can use L'Hopital's rule. If I had if this fraction was going to something else, right, like maybe 0 over infinity or something weird like that, then I really can't use it, right? So you have to think more deeply about how to use it. Okay, so, but here we have infinity over infinity, so we can go ahead and use L'Hopital's rule, right? So this limit is the same as the limit as x goes to infinity, and I'm going to go ahead and take the derivatives here. And actually, before I do that, I'm going to write down that I'm using L'Hopital's rule to get this equality. Okay, so if we think about the derivative of ln of x, right, that's the derivative that I introduced right at the beginning of the video. So derivative of ln of x, that should be 1 over x. That's what's in the numerator. And then derivative of x in the denominator should just be 1. Okay, so do a little bit of simplifying here. Limit as x goes to infinity. 1 over x divided by 1, that's just 1 over x. Okay? And then if we think about this, right, 1 over x, what happens when I take the number 1 and I divide it by bigger and bigger numbers? Well, that should just be going to 0, right? So this is 0. Okay? So then the answer I get for number 3 here is this 0.